we talk about ML production monitoring, and then the next week, actually AI Camp organized AI Summit, with a great speaker from, Facebook, Google, and other places. So, and then the next month on the March 11th, we have another talk on the ML infrastructure given by Josh Tobin, who's the currently CEO of new startup, and also the instructor for deep learning, full stack deep learning class at Berkeley. So, so that's our coming, coming event. Please make sure join that. With that, I'm gonna stop sharing. So, Alexandra, you probably want to share your screen. So tonight we have Alexandra all the way, giving talks from London. He's a chief architect out of the. Let me just make sure I don't read it incorrectly. So. Somehow the meetup page also stopped me. But he's a director of technology at Sheldon Technology, and also the chief scientist at the one of the institute. Maybe Alexandra give you more details, introduction about yourselves. And today he's talking about the production machine learning monitoring. Alexandra, please take away.
Awesome, perfect. Yeah, thank you so much, Chester, and really great to be here. Today, we're going to be delving into a very interesting topic, production machine learning monitoring principles, patterns, and techniques. So today's session, because it's happening completely virtual, we have people from all around the world, and similarly, we have the benefit of this asynchronous chat functionality. So as I'm presenting, feel free to ask questions on the chat or share your thoughts on the chat, and I'll be able to reference them or answer them either as I go or at the end. At the end, I'm also going to be able to expand on some of the areas that perhaps have been more interesting and more sort of trending in the chat. So please do feel free to add questions. I think Chester mentioned to send the questions on the Q&A. I'll be able to see that, but also if there's a discussion in the chat, I also have that open. So just as a heads up, this overview that I'm going to be giving today, because it's a presentation, you're not really going to have time to jump in and try to write all the code and try it yourself. But if you want, and if you're curious, you're able to try this link in the corner, bit.ly/prod-ml. This link contains a blog post that basically delves into minute detail on quite a lot of the topics that we're covering, to the point that you can implement it yourself. So with that, let's dive straight into it. So a bit about myself. My name is Alejandro Salcedo. I am engineering director at Selden, chief scientist at the Institute for Ethical AI, and governing council member at large at the ACM. To tell you a bit more about each of this, Selden is an open core company, which means that we have primarily an open source product with an enterprise built on top. We have basically one of the most popular Kubernetes-based machine learning orchestration frameworks, which is basically the open source tool that we'll be using today for some of the examples. The Institute is a practitioner-based, UK-based think tank that focuses on highly technical research on developing frameworks for the responsible development of an operation of AI systems. And as a heads up, we are part of the LFAI, the Linux Foundation, which is a great thing given that we can be involved on the very practical level. We recently published the 8 principles for trusted AI for the Linux Foundation, which is aimed for open source projects and open source practitioners that want to adopt a Northern Star in their own projects. So please do, contribute, get involved. To today what we're going to be doing is we're going to be covering a couple of things, including the motivations for machine learning monitoring. Why do we want it? Some principles to approach efficient machine learning monitoring and effective machine learning monitoring, patterns that you can adopt for production machine learning monitoring, and hands-on examples showcasing some of these techniques. So it will be very much a very heavy concept-heavy presentation, but as I mentioned, if you want to delve into some of the details, there is also that blog post that I mentioned. And basically, yeah, the examples and links, I think it's easier to find them basically on this link, bit.ly/prod-ml. And also the code examples and everything is there. It's all centralized. So now let's dive into the motivations. So production machine learning systems are complex, right? And why is that? That is because of a broad range of reasons, including the specialized hardware involved and the orchestration managing this hardware. You may have models that may require specialized hardware, like not just GPUs, but even further like TPUs. There's also nuances where you may require large amounts of memory for very big models, tens or even 60s, 70s, 80 gigabytes of RAM or more, or potentially a heavy amount of CPUs. That, of course, orchestrating that infrastructure that requires a broad set of heterogeneous components. There is a lot of complex dependency graphs of how data flows between each of these components, making sure that the data can be managed and the lineage of that data can actually be traced, not only through the steps, but through its life cycle in a way that is not just relevant for auditability, but it's also relevant for reproducibility, right? And then that goes into the reproducibility of components, making sure that you're able to not only run something, but the fact that you're able to reproduce it and ensure that just because it is a Saturday, there's a different result. Ultimately, this in itself is a challenging principle. And compliance, which basically means adopting some of the high-level infrastructural IT requirements that are necessary outside of just AI and the models to be able to make sure that the operational processes around your AI systems are fit for purpose, are following the right, have the right touch points in place and the right level of human, I guess you can put it. So from that perspective, that also has changed the perspective that machine learning models, the biggest bulk comes from training the models, the complexities that are involved on just getting that model into a reasonable, not just accuracy, but a reasonable metric that makes that good performance for when it actually sees inference data. But one thing that is now a growing consensus within the machine learning community is that the life cycle of the machine learning models only begins once it's deployed, right? That is when you actually start seeing the complexities of things like data drift, things like perhaps just infrastructural challenges of the microservices that are facing some either scaling complexities or scheduling challenges, et cetera, retraining of components, and a broad range of other things that we're going to talk about. But in order for us to really see what this looks like in practice, what we want to do is we want to actually take a hands-on example. And what we're going to be doing is we're going to be seeing what is the whole end-to-end life cycle of a model once it's been trained and once we want to actually make it available for business consumption or for just consumption. So we're going to be seeing how to deploy a model as a microservice. We're going to be able to see how you can send predictions to this model. We're going to be able to see how you can actually not just send predictions, but send annotations or corrections. And with this very basic sort of interaction, building an entire stack that allows for efficient, reliable, and robust monitoring, not just for the requirements that are brought in by software, but also by the nuances that are introduced with machine learning. So machine learning metrics. And that's where it starts getting really interesting. We're going to be taking a familiar model. So we're going to be seeing the CIFAR-10 classification. I actually have another older sort of overview of this end-to-end use case that uses the iris classifier, which is basically a tabular example, a tabular classification model. So if you're more interested on tabular as opposed to image data, you can actually see that other example and see the full end-to-end that we're going to be covering today. What is the CIFAR-10? So this is basically a classification data set that many people that have worked in data science would have come across. Even it's quite popular on simpler examples. It consists of an input, which would be of the type of an image, and the prediction would be a one hot vector that specifies which class does the model think the input is. In this case, it's going to be a truck, right? So is the last class, the number 10. So what we're going to be doing for being able to work with our model, we have to, of course, well, we don't care right now about training our model, right? We have already trained our model. In this case, the model has now a good accuracy, precision recall, specificity, or specific metrics. And we want to just, deploy it, and we want to manage it in production so that other users, other applications can consume it. So in this case, what we're going to be doing is we're going to be, importing TensorFlow and the data set, right? So the CIFAR-10 load data. So this is basically all of the training and test data. Of course, we don't really need the training data at this point, and we're going to be just using that to interact with the model. And we're going to be using a couple of other libraries that I'm going to introduce later, besides Lubuntu Core. Alibi is the tool that we're going to be using for explainability, outlier detector, concept drift. In this case, we have an easy way of fetching that model, right? So we're just going to download it locally to test it. So we're going to be getting the ResNet32 model, which now we then can use to just run predictions, right? So in this case, we basically have the pixels of the truck, right? So this is the image of the truck, and the prediction will be the actual class, right? So that's what we're seeing here. Now, how do we turn this local piece of Python into a productionizable component? We're going to be doing this using Lubuntu Core. So Lubuntu Core is a platform that I mentioned briefly, open source framework that allows you to convert your Python code or machine learning model binaries, so the pickles. If you were to just take this model and export it as a pickle, that's what basically we would be able to use. So with either the prepackaged model servers, which provide sort of optimized processing for TensorFlow, scikit-learn, the usual suspects, or if you have something super custom and you want to, I don't know, wrap a data robot model or a H2O model or something like that, a Java-based or C++ based component, you can use the language wrappers to convert that specific component into a fully fledged microservice with a REST, gRPC, and Kafka API. So we'll see what that actually looks like in more sort of like intuitive perspectives. The key thing is that with Selden, not only you're able to convert, containerize a model and deploy it as having a single API, but you're able to actually build complex graphs as part of your infrastructure. You can have perhaps a multi-arm bandit that uses an online sort of updating of its own state to send the requests that are being sent to the model to the best performing model. So we actually have tons of examples in the repository which you can try yourself, all the way from multi-arm bandits to simple models with TensorFlow, scikit-learn, XGBoost. And ultimately, what we're going to be focusing in this session is just on a simple model that we're going to be deploying. What that really looks like, again, if we're using the language wrapper, we would just have to actually define a Python class or Java class or C++ class, depending which language wrapper you use. This class has to have a predict function. This is the function that gets called when you send a REST request or gRPC. Whenever you actually send a data to the microservice, it actually gets passed through this function. You can put whatever logic you want. In this case, what are we doing? We're basically going to take that model that we have here, that model predict. We're going to be loading it, right? This is basically just loading it locally. This is basically just like a file with the binary next to it, loading the pickle, using it when you send the prediction, and then there's other features to expose metrics and whatnot. The key thing is that then you can use the utilities to convert the code into a microservice. But what is simpler, instead of having to use a language wrapper, you would be able to just use a prepackaged server. The prepackaged server, and interestingly enough, we just had a question that comes at the right timing, which is how does Selenium compare to other frameworks like BentoML or MLflow? So the answer is similar to TensorFlow. Selenium actually uses, for TensorFlow models, the actual official Docker image for TF serving. Similarly, we actually have a MLflow server wrapper, right? So you can actually just provide your binaries of MLflow exports that actually get converted into a fully fledged microservice. And we have actually seen also some people deploying models from other wrappers, as Selenium is more of a Kubernetes orchestrator, right? So once you actually containerize your model or specify the artifact, you can either test it locally by sending some requests, or you can deploy it to Kubernetes. The way that you would deploy it is using the custom resource definitions. This is an infrastructural abstraction that extends the Kubernetes APIs, that introduces a new concept, which basically says this complex machine learning concept of a model is now simplified into an infrastructural component that is just basically a black box with a expected endpoint that receives data, right? What is inside is going to still be highly complex, potentially very advanced data science type models. But from that perspective, it is about abstracting complex machine learning concepts into simple infrastructural Lego blocks, right? That then DevOps can manage and not require data scientists to have to manage all of that DevOps complexity. What we have here is basically that model URI, which instead of just having that pickle locally, it would be on a Google bucket or an S3 bucket. And we can specify the implementation, which is the prepackaged server. In this case, basically, it would just load this artifact on TensorFlow serving and would expose it through the API. What then allows us to do is we can actually check that when we deploy it, it's actually deployed, it's running, and we actually can send a request to the automatically created path, right? So in this case, the name of our model is CFAR10. So here we can actually pass it to Selenium / namespace / name of your model prediction, right? So that's basically it. And we can see that we would get the same expected result as if we had run it locally, right? So the input locally was an array of floats that contains basically the pixels, and the prediction is basically the class. In this case, we're seeing the exact same thing. We're passing this as the request, right? And then the response is also just the class, right? So basically, this is all that we needed. We've now containerized the model. But the challenge is not just to put a model in production, right? That's, again, the easy part. The hard thing is to make sure that it is scalable, robust, and reliable. And what I mean by that is that you're never just going to deploy that model and just go to the pub on the Friday and have all the beers and everything is good and dandy and happy. Normally, you may have to actually publish multiple versions of a model. You're going to have to perhaps promote that model across a different environment. You may actually require understanding whether there's divergence on the performance. And from that perspective, at each of these stages and changes, there's lineage that needs to be taken into consideration. So let's have a look at the anatomy of production machine learning. So one thing that we would always have that is actually, as we already stated, happening before Selden begins is the experimentation stage. This could be your Jupyter notebooks, your ETL workflow managers to perform your hyperparameter tuning or training or evaluation. And in this specific case, you would use training data to produce trained models, right? So that's something that I'm conscious we're oversimplifying, but this is kind of like where the intuition can go. Now, in order for you to be able to make use of these models that have been created, these artifacts, that's then where Selden can be programmatically triggered through either continuous integration or other type of ETL pipelines. So this is for building images, retraining models, or processing batch prediction, as we will see later on, ultimately with the objective of deploying those models in the same way that we saw, but in a scalable way. And the key thing to mention is that once you then deploy the models for either real-time or batch processing use cases, this in itself is not just monitoring of models. This is not going to be just accuracy of data. This is all on live data, on inference data, on unseen data points that may not have labels and or that the labels may come asynchronously. And that's why for us, we also want to make sure that there's the connection back to the full cycle. And as we will see, the main challenge that we see is that with Selden, it's not just about deploying one model, 10 models, 100 models, but it's really about achieving scale that enables entire organizations to manage their production machine learning complexities and ensure that data scientists can do data science, DevOps can do DevOps, as opposed to data scientists having to write Flask wrappers and then manage the CI pipelines to deploy their models and manage them in production. Now, in regards to the actual categories for monitoring, there are 4 that we're going to be delving into today. There are performance metrics and tracing, statistical performance, and model performance, I think is more accurate, drift detection, outlier detection, and explainability. And perhaps you may have come across all of these topics in the context of the experimentation side, right? Perhaps you may be running an explainer algorithm in one of your existing models in your Jupyter notebook to explain how it behaves, or you may want to run some drift detection data on a batch, scheduled job on offline data. But what we're going to be seeing today is how this would work with production, live incoming data. And then, of course, plus all the relevant alerts, if you want to then trigger actions that follow on from particular rules on that monitoring components. So the first one is the performance monitoring principles. So this is monitoring the performance of your running machine learning services, right? And this is very much akin to the microservice monitoring, right? Of course, adopted into machine learning, but it is pretty much just microservice monitoring. This is to identify potential bottlenecks or runtime red flags and debug, diagnose unexpected performance for machine learning services. So examples of performance monitoring could be things like requests per second, latency per request, CPU memory and data utilization, things like distributed tracing to see how long each sort of hop takes in regards to latency, custom application metrics that you may want to add. And from that perspective, the performance monitoring patterns that we have been able to adopt is that every machine learning model that you deploy will have a couple of things. It will have metrics that are coming out of it, and it will have not specifically logs, but it will have inputs and outputs, right? And we're going to be covering later on, not just inputs and outputs, but also feedback, annotations, etc. But from that perspective, what we need to make sure is that each of those components, regardless of how complex they are inside, regardless of what neural network architecture they're following, ultimately they will have this sort of standardized interfaces to produce metrics. In this case, you would be able to see the request per second, latency, CPU usage, etc. And then in the other side, you would be able to see all of the inputs and outputs being stored. Why would you want that? The reason is not just for auditability, but also if you wanted to perhaps replay a particular data stream, and I know this is not a stream in the context of like Kafka and actual queues, but particular sort of start and end of, let's say, last year, this is what would then allow you to then replay a specific particular data set. There's, of course, also some work that we do to ensure that there is full reproducibility of the models themselves, so that there is basically a sort of snapshot of each change that is done on your actual deployed model, that ultimately then integrates with some of the components that were mentioned, like ML flow, etc., etc. So this is some of the production monitoring patterns that we know also scale across large sort of setups. Now, when it comes to this component of the inputs and outputs, the way that we were able to also build this capability was not by just pushing directly to what this, in this case, is Elasticsearch. The way that we've approached this is through the concept of a serverless eventing architecture. And this, sounds like, all of the buzzwords cram into one single name. And it is basically that. But the key thing here is the eventing architecture. This means that every single data point that goes to the model, what happens is that it gets forwarded to the eventing architecture. And this eventing architecture basically allows you to subscribe different advanced monitoring components to be able to do things with that inference data asynchronously, right? And this is going to be very powerful because this is the foundation of a lot of the foundation architecture for a lot of the production monitoring components that we're going to be covering. And this is important because if you have like 10 outlier detectors or 3 outlier detectors and 1 drift detector, this then allows you to have this very complex processing without hindering or affecting the performance of the model, right? You wouldn't want that suddenly the actual inference is not performing to the optimal because you are running an explanation request, right? You wouldn't want that. So that's basically the context of this. Now, we're going to be talking about the rest of the more machine learning specific monitoring patterns. But that serverless architecture piece, you will see how it will come up again and again. The first one is the statistical monitoring principles. And I guess a simpler way to call this is model performance metrics. So in the case of our classification use case, this will look like accuracy, precision, recall, specificity. But of course, for regression type models, it would be something like RMSE. We can also have for other cases, more specialized components like KL divergence. And you will see how we've approached this so that it can be abstracted in an interesting way. But model performance boils down to monitoring specific machine learning metrics. This is more in the context of what we call stateful metrics. And we call them stateful metrics because you cannot calculate a lot of these ones until you get the annotations, the corrections of the unseen data points. So that means that it requires some sort of process asynchronously of people going back and saying, hey, for this prediction with this unique request ID, I will give you the correction. I will give you the sort of truth value, right? So now you have the truth value, give me insights, right? So from that perspective, it is used with collected labels and can be used to benchmark the performance of the models. Now, this as I mentioned, is like raw metrics like true positives, true negatives, false positives, false negatives. So it predicted this value and the truth value is the same, true positive, etc., etc. If it's not, then false positive, or depending on the type of classification data. And from that perspective, the way that we have been able to approach this is with the model performance pattern. So similar to how we saw that sending inference data sends this to the serverless eventing architecture and forwards it to store the inference data. This inference data contains a unique ID, right? Each request gets its own request ID, and the client gets that request ID back. What then is possible to do is that any external domain expert or another perhaps individual that is part of that operational process of the production machine learning deployment would be able to then send correct labels for that particular request ID. That uses the same serverless eventing architecture, but the only difference is that instead of going directly into the Elasticsearch, it would go into the metric server, right? And this metric server is basically a component that is exactly, or not exactly the same, but very similar to that of a model, right? So it is also a Python wrapper. You add your own logic. You can add and expose any metrics you would want, with the ultimate objective to be able to perform any custom calculation you may want. In this case, with the CFAR dataset, it would be a very simple sort of one hot vector comparison, right? Is the truth value with that request ID the same as the value provided? Based on that, expose the respective metrics. And particularly in this specific case, in the blog post, you will be able to actually even see in your Grafana dashboard the precision, accuracy, recall of the model as you provide corrections to the model itself. So that's basically the overview of the statistical monitoring pattern. I mean, it really is quite intuitive if you have sort of calculated the performance of a model in your experimentation phase, right? So this is really just abstracting that and providing it in a way that can scale to multiple components. Now, let's go to the second part on explainability monitoring principles. So explainability is an interesting one, given that the core focus is to provide human interpretable insights for model behavior, right? So this is introducing use case specific capabilities, which may require domain expertise. And this involves not just an intuition for specifically the moment where you get the explanation, but it provides further statistical metrics like trust scores or performance thresholds that, interestingly enough, could also still be used as a sort of monitoring component, which ultimately would be processing data and interacting with the model. And the reason why this one is particularly interesting is because explainability has a broad context. It can be local, it can be global, right? That means that it actually acts upon a single data point or a broad range of, or the entire sort of data set. It can be white box or black box, which means that for black box, it interacts only with the inputs and outputs. It can be for classification, for regression, for tabular, text, images, etc. And what we're going to be using for this example is this tool called Alibi. Alibi is a explainability tool set that contains a broad range of different explainability techniques that you can use with any black box and white box machine learning models. And the way that this looks like, I guess before actually diving into what it looks like from a monitoring pattern, what this basically looks like from a model is, instead of actually just calling a prediction, what you would be able to do is to pass the model itself to an explainer, right? And request a prediction, right? So request an explanation. And what the explainer would do is it would interact with the model as a black box. So it would take the input and it would try to understand what are the features and that by changing the least possible, it could change the output, or conversely, that would actually have the biggest effect, getting an insight of the feature importance of all of these components. And of course, there are a broad range of talks that dive into the concept of explainability. I actually have one, if you're interested, that dives into the different techniques. But for this particular context, what we want to understand is how do we take the concept of an explainer and convert it into something that not only can be deployed, but that can interact with all of these other different components that we've been talking about. The way that this would work is that, as we saw, we have a machine learning model that has a prediction endpoint. When it receives a input, it would respond with an inference sort of response. But the explainer, on the other hand, when it receives an input data point, instead of providing an inference response, it would actually interact with the model in the same way that it would do in your local Jupyter notebook, but instead, interacting remotely by sending REST requests instead of just passing it to the Python function, with the ultimate objective of reverse engineering and identifying a relevant explanation depending on what technique you're using. And the way that the explainer is deployed is in the exact same way that we deploy the model. So you would actually just provide the explainer binary, and the microservice would then be created for you to be able to then send requests to that particular explainer. And the cool thing about this is that a lot of times organizations and people may not realize that, even though from an intuitive perspective, if you have a model in production, deploying an explainer, being able to explain that model reduces risk, right? That's intuitive. Nobody's going to argue with that. But the challenge is that by putting an explainer in production, you're putting another complex data science component in your production infrastructure that introduces risks in themselves. And I think this is why it's important to ensure that, similar to the components that we already said, models have metrics, models have requests per second, models have these requirements. The explainers, the metric servers, are the same architectural pattern as a model. They have metrics, they have the ability to connect to other advanced monitoring components, which in turn, it has also reproducibility. It stores all of the inputs and outputs. It has the lineage of every change that happens to your explainers. And the key thing here is that this is what then allows you to not just have one model, one explainer, but maybe hundreds of models or thousands of models, hundreds of explainers, hundreds of et cetera, et cetera. And there's an interesting question, which is asking, do you have any recommendation for tools such as Kubeflow and any paid vendor tools you recommend from your experience, i.e. NVIDIA has Triton Inference Server? So specifically for this, I mean, I think particularly in the open source side, there are a broad range of different tools, from the ones that you've mentioned with Triton Inference Server. Interestingly enough, also Selden provides the ability to deploy with Triton for any ONNX and PyTorch models. So you're able to actually use it out of the box in the same way that I just explained. In the underneath, you would actually be just running Triton or TF serving. So it's an abstraction. So you get those benefits. Also, Selden is part of Kubeflow. So Selden Core is part of the Kubeflow ecosystem. Both Selden Core and KF serving are the serving component of the Kubeflow project. And from that perspective, it is yet another very recommended tool. Of course, Kubeflow falls in the experimentation side when it comes to Kubeflow pipelines, but then it has other components that fall on other different areas. So that's basically, a high level overview, and we can delve into that a bit further in the Q&A. So that was on the explainers. Now, again, if you want to actually try it, the blog post has all of the code that you can try yourself. But this is more for the intuition. Now, the outlier and drift monitoring principles. So outlier detection on production inference data to be able to detect anomalies. This may most often be on single data points, right, that are coming in from the model, either the inputs or the predictions, for you to be able to identify whether there's an anomaly. And then similarly for drift detection, it is potentially detecting drift in that production data and coming to the model, or using concept drift to be able to actually leverage the inputs and outputs of that. So in these examples, what we're able to do is we're able to actually add some Gaussian noise and motion blur and brightness to original images in the CIFAR data set to actually send it to the model, and then see how outlier detectors would be able to pick that up and say, hey, it's an outlier, right? The key thing with outlier detection is that there are also different attributes to consider. There is a scope, whether it's acting upon the input or the output, whether it is a supervised or unsupervised algorithm that is being used underneath for your outlier or drift detector, whether it is classification, regression, etc., the data type for tabular images, etc. And from that perspective, it also has its own, pattern, right? First, let's talk about the outlier detection pattern. With the outlier detection, what you have here is that every time that you send data to the model, it forwards it to the serverless eventing architecture. Now, what we would have here, instead of having a metric server, we have an outlier detector component. This outlier detector component, in the example, it's using Alibi as well, Alibi Detect, which is a compilation of state-of-the-art algorithms for drift detection, adversarial detection, etc. For this particular example, what it would be able to do is to actually run that incoming data and process through its own internal outlier detector model, and basically store whether the data set is an outlier or not, right? So from that same perspective, the outlier detector is built in the same way as the explainers, as the models. You basically deploy it by just providing a bucket, right? An S3 bucket or a Google bucket containing the binary, the pickle, which makes it much more easier to interact with. So from that perspective, similar to the explainer, you now also have an advanced machine learning component that works on an advanced machine learning component, right? So it is important to ensure that you have the same level of sort of like safeguards on top of that component. And the drift detection is similar to the outlier detection, but the difference is that would actually act on a window of data, right? It would not just take a single data point and run it through, but instead it would actually take a batch size of either a tumbling or a sliding window, and the actual results in this case would be exposed to the metrics themselves, right? So you would be able to then see what the results are by looking at what would be a Grafana dashboard. But in the blog post, you will see that all of these examples can actually be visualized in their respective Grafana dashboards. Even this one that stores the data in Elasticsearch, it also exposes the metrics to Prometheus so they can be visualized. Right, so that's basically the key patterns for drift detections, and I definitely encourage you to try them. I mean, it's actually a big Jupyter notebook that is provided with the blog post, which you can literally just run through, and you will be able to run all of those things end to end. So it'd be great to hear your thoughts as well. There's an extra note. We're not going to be diving too much into this because the patterns would be similar, but adversarial detection is also a key component to be able to identify potential malicious players in the system that may be aiming to reverse engineer, or not reverse engineer, but try to kind of like trick your particularly deployed models. There is an interesting sort of set of techniques that also the Alibi Detect library provides that you would be able to try in similar architectural patterns that can be deployed from that perspective. And just to kind of like give you some food for thought, the reason why this serverless architectural patterns are so important is because this allows for much more rich and complex setups where perhaps instead of just having a model, forwarding the requests into a metric server that is giving us the accuracy, precision, recall, or the true positives, true negatives, etc. Instead of just having that, we could actually have on top of that metric server another drift detector that is acting on top of that accuracy metric, for example. And then you would be able to detect whether there is a drift on the accuracy itself. And this is extremely interesting because then this becomes more of something that can be built on top of each other in a way that it's not highly complex and challenging small, highly specialized pieces that require a lot of domain knowledge in order for them to be used. So that's basically the overview. I think, yeah, we have a couple of questions coming in. So to wrap up, today I covered some of the motivations for machine learning monitoring, the principles for efficient monitoring, some patterns that you can follow in regards to the architectural ways of thinking about how models can be scalable in production, and then some hands-on examples that in this case, it was probably more of just the high level intuition, but the blog post and the Jupyter notebook will allow you to actually run it end to end and visualize each of these different components yourself, which makes it all that more exciting. Again, well, the actual links are on the top right. So I'm going to just go to the first slide. And so the code and the slides, yeah, you can find them on there. So with that, yeah, I thank everybody for your time, as well as Chester and the organizers. So I'll just pause there, pass it over back to Chester, see if there's any questions and any further sort of discussion. Mm-hmm.
Thanks, Alexandra, for discussing the patterns for the monitoring. So we have a few questions kind of mixed in the chat as well as the Q&A. So I'll go to I think there's a chat that has a question. So how does this Selden compare to other framework like Bento or MLflow?
Yeah, so yeah, I think I only touched upon briefly before, but maybe worth sort of just mentioning how Selden in itself is an orchestrator platform in Kubernetes that aims to provide more of that architectural abstraction. And underneath, it actually provides access to use the MLflow model server, the Triton model server, the TensorFlow serving model server. So depending on what artifact you're trying to deploy, basically Selden is kind of like an abstraction layer to be able to just use the best underlying framework for that use case. And if you have MLflow models, encourage you to try the MLflow server. Mm-hmm.
Yeah, the other question also from the chat is that, do you have any recommended tools, such as the Kubeflow and other paid vendor tools you recommended from your experience, example, NVIDIA as a Triton inference server? So I guess you covered some part already. So
yeah, so I mean, I think for that, I actually do have a very good sort of suggestion. So we actually curate a list of production machine learning tools to deploy, monitor, version, and orchestrate your machine learning. And in this list, basically, you can find tons of tools, as you mentioned, like Kubeflow, but for every single different area. So privacy preserving ML, model versioning, model training orchestration, model serving, adversarial detection. So I recommend you checking it out. So if you go to github.com/ethicalml, you'll basically find the first repo there. So that's what I would recommend, actually. Mm-hmm.
That's great. Can you share that on the chat?
Yes. So for easy remember, yeah, ethicalml, and I'll just share it on the chat, actually.
Yeah. So the other question coming as Mr. Weibo Tao is that it says Sheldon seems really useful in the big corp where there are tons of data scientists and developing many tons of models. For a smaller team like garage state startup, do you think it's still worth it for them to spin up a big Sheldon clusters? If not, what are the alternatives, in terms of effective monitoring ML in production for a small setting?
Yeah, that's an excellent question. That's an excellent question. So what we have seen is something very, very similar to what your assumption is, which is that Sheldon tends to be most brings the most value when it comes to contexts where you have more than, let's say, 10 models that you're expected to not just deploy, but have a continuous pipeline to have continuous delivery of models, right? So if you have, let's say, even more than 5 models, that's when the value starts becoming value starts actually converting. But if it's actually a organization that is much smaller, just has maybe a couple of models, their stack is not super sophisticated, and the stack is not Kubernetes based, then probably it's not going to be even a good choice to just bring Kubernetes into that mix. But if you already have Kubernetes there and you have a couple of models, then it would still bring value, particularly as it's the question of, should I be deploying my web server in sort of a bare metal instance, or should I be deploying it as a Dockerized microservice in a container orchestration platform? The latter is always going to be much more scalable. If you have the capabilities, it's always going to be potentially better insight. But it does have, the biggest dependency is that Kubernetes layer, right? Kubernetes is the biggest steep learning curve. If you already have that in your stack, yeah, adding Sheldon is a no-brainer. Mm-hmm.
Got it. Yeah, so another question, says, thanks for the presentation. Are the explanations logged, example, anchor results? Can we define a customer metrics on top of these that can be tracked? So I'm not quite sure what it is. Are the explanation logged?
Yeah.
Anchor
Yeah.
results?
No, I think that's a great question. So the answer is yes. In the example, we don't show how you would actually log the explanations, but when it comes to the actual microservice components, that's why I always emphasize on the point about the patterns. Each of these components, all of the inputs and outputs would get stored, and all of the changes would also be reproducible. Now, the key thing to take into consideration is that with explainers, you not only have the initial explanation request and the explanation result, but you may also have thousands of requests that get sent to the model. So you may or may not want to also store all of those thousands of requests that are very much just metadata to get a result. So for the first part of your question, yes. For the second part of, can you add custom metadata on top of it? The answer is yes. So you're actually able to add metadata to each request, and you're able to also add any logic that appends metadata to the request itself, so that you're able to ensure that is also stored and logged for further retrieval. An example where this is useful is in the case of with Sheldon, when we actually enable for batch processing as opposed to real-time requests on the REST API. Batch processing requires that asynchronous retrieval of the results. So you need to add a extra identifier that perhaps would map into your internal system, so that you're able to know which request or which response did that actually map into. So that's basically to the second part of the question. Yeah.
Got it. Any other questions? If no more questions, thank you, everybody. Thanks, Alexandra, for the great talks. And so this is the topic, as I said, it's like everybody is have an eye on, and a lot of interest from the community. So I really appreciate it. He spent his evening in London and give us a talk in San Francisco time. Thank you so much. This is really helpful.
No, thank you for having me, and thank you everybody for joining. Yeah, I hope if there's any sort of thoughts as you try the examples, please do feel free to open an issue on the repo.
Great, great, will do. Thank you, everybody. See you next time. Okay, bye-bye.